Hi everybody, it's Mrs. Beachy from your WCA Physical Science class. And this is part 3 of our Semester 2 final exam review. It should be the last part of it. So we stopped with most energy from the sun or most renewable energy comes from the sun. We've also looked at how energy and mass are related to each other, and one of the things that Einstein gave us was the formula E equals mc squared. And this tells us a few things. It tells us that energy is released when matter is destroyed. For example, in the combination or combining of hydrogen atoms to yield helium, and it releases a neutron. Some of that mass is actually converted to energy, and that's how that energy is given us in that reaction. It says that mass and energy are equivalent. We're just looking at them two different ways, and so the law of conservation of energy must be modified to state that mass and energy are conserved in any process. Modified. So all three of those things are true. We also learned about temperature. So temperature will rise, and that will relate to a rise in thermal energy. Talked about conductors of heat. Metals are primarily the best conductors of heat, and you guys know that. I mean, if you touch a metal spoon in a hot pan of boiling soup, it's going to be painful likely. So we talked about a heat pump. A heat pump is something that basically reverses the natural laws of thermodynamics, but it requires energy. So it requires energy to move heat from cold to hot. So this is how air conditioners and stuff will work. So it's moving heat from a cooler area to a hotter area, which is a kind of opposite the natural flow of things, and it just further cools it down. But it doesn't require energy or work to do that, whereas the other processes not require energy. We talked about transverse and longitudinal waves. Transverse wave looks like a T, capital T. It's going to propagate in one way while it's oscillating in the other way. Okay, so that is what a transverse wave looks like. Longitudinal wave is like a lowercase l. It's going to, actually, it's probably more like a line, like this. Because it's actually oscillating back and forth, and it's also propagating back and forth, okay? This is also called compressional. And we see those in sound. Transverse waves we see in electromagnetism, light, and many other types of waves, water waves, seismic waves. The velocity of a wave is equal to the frequency times the wavelength. So if I double the wavelength, the wave frequency must be halved in order for the velocity to be the same. So if the speed does not change, if you increase the wavelength, the frequency is going to go down. Think about how that makes sense. If I increase the wavelength, fewer waves are going to pass by a single point in a second, but the velocity remains the same. You know, I mean, it's just how many times does it oscillate in a second or pass by a certain point in a second. Frequency is going to go up as wavelength gets, or frequency, excuse me, goes down as wavelength goes up. They're inversely related to one another. The highest frequency the human ear can hear, and these are just mostly children, is 20,000 hertz. That's pretty much the upper range of human hearing. If those of you who were in class with me on that day, we did that little demonstration. You remember that that's the highest, with the hearing test, that's the highest we went up to. So light can be a particle and a wave. A particle of light is a photon. Excuse me. Excuse me. Sorry about that. Totally unexpected sneezes. When you look at wavelength, excuse me, shorter wavelengths are equal to higher energy. And shorter wavelengths, this is of all electromagnetic waves, equals a higher frequency. Remember, there's more waves that pass by the point in a second because they're smaller. So highest energy waves are gamma rays. We also looked at light emitting devices, not LEDs specifically, but all sorts of, types of bulbs and stuff. Incandescent light bulbs have solid metal filament in them, so it's heating up a metal. We have halogen light bulbs. Which, as it kind of describes, it uses the metal tungsten, which is actually what the solid metal filaments are made of in incandescent light bulbs, to heat up a gas in the halogen family, and that glows. Oops. And then we have neon bulbs, which is the gas neon. It's an inert gas, but when given energy, it produces a red light. And then we have fluorescent. And fluorescent uses like mercury and phosphorus, and it basically gives it energy, and that also produces a light. It's more of a bluish white light, though. Let's go ahead and move this down. So electric fields are proportional to the quantity of charge. In other words, if your charge is like 5 plus, for example, it's going to have a stronger electric field than if the charge is like 1 plus. So if it has a positive charged field and it's only one single charge versus 5 times the charge, that's going to produce a greater field. Look at Ohm's law. Ohm's law says that voltage equals current times resistance. Remember that current is amps or amperes. Resistance is ohms. Okay, so that's, and voltage is just volts. That one's not a hard one to figure out. So you can solve a problem regarding figuring out the resistance in a circuit, or the current, or the voltage, depending on this formula. You also got to remember that you have to take into consideration whether it is a parallel or a series circuit too. We also have electrical power. I apparently didn't spell that one correctly. I missed a C there. Power is measured in watts. Okay. Power, we've talked about power before. It's work divided by time. In this case, work is basically a measure of energy. In this case, when you do a bunch of kind of solutions of what is an amp and what is a volt and things like that, you come up with a formula that voltage power equals voltage times current. Power equals voltage times current. That gives you the power in watts. We looked at electromagnets using a nail and like a copper wire wound around the nail. We know that the iron makes it a stronger magnet, but we also know that if you create more loops, or if you increase the current, it's going to make that magnet stronger. So make the magnet stronger by making sure it has an iron core, more loops of wire, and increasing the current. All those things affect the strength of the magnet. We talked about the difference between digital and analog. Digital is basically pulse current in a series of ones and zeros. When we look at the Earth is a large magnet and strongest field near the poles. Almost there. A transformer transforms energy. That's kind of hard to remember, huh? So they decrease voltage or increase them. All right. Looks like I actually am gonna have to do just one more partial part here, part 4. So bear with me. We'll be back with part 4, and just tune into the next video.